Hey students, welcome back. This video is going to be discussing Chapter 1's Lesson 4, Prime Factorization. So get your notes ready, get your learning target going in here pretty soon. In our math books, we should be looking at page 26 so you can see what examples I'm pulling from. And our learning target today is going to say, I can write the prime factorization of a number. So upper right hand of your journals, we'll go ahead and get that in. I can write the prime factorization of a number. Again, just another reminder, you can pause and go back and go forward faster anytime that you need to on these videos. So to start with, we're going to talk about some vocabulary terms. The first one is factor pairs. So we'll write down the words factor pairs. We'll talk about those. So a factor is a number below a larger number that can go into it evenly. And if I'm talking about factor pairs, it's going to be two numbers that when you multiply them together, it gives you that larger number. So the best way to write that out in words is going to be numbers that can be divided into other numbers with no leftovers. If this is confusing to you, we'll do a little mini example here. If I'm thinking about the number 15 as my starting number, and I want to list the factor pairs of 15, we're going to ask ourselves, what are the pairs of numbers that multiply to 15? So we could multiply 1 times 15. So that's a factor pair of 15. You could also multiply 3 times 5. That is another factor pair of 15. So those are factor pairs of 15. So dealing with that, we'll look at example 1, because in example 1, they're asking us to use some factor pairs. So we're still looking at page 26. Example 1 says the brass section of a marching band has 30 members. The band director arranges the brass section into rows. Each row has the same number of members. How many possible arrangements are there? So let's take out some important information here. So what they've told us is the band has 30 members. So that's how many total people need to be in all of these rows. Each row has to have the same amount. So each row needs same amount. So you can't have a row with a different number of people in it. And then lastly, how many arrangements can there be? So we want to figure out how many different arrangements. And another way of saying this is we want to list the factor pairs. So listing the factor pairs is kind of like we did up here. We have this starting number and we list all the pairs that would go into it. So our starting number this time is going to be 30. So we're going to start with this 30 and we're going to list all the different ways that we could get to 30. So we could have one row of 30 people. We could also have 30 rows of one person. You could have 2 rows of 15 people, and you could flip that around and do 15 rows of 2 people. You could also do 3 rows of 10 people, and flip that around 10 rows of 3 people. And let's see, you could also do 5 rows of 6 people or 6 rows of 5 people. I think that's all of them. So if we look, we have a total of 8 different factor pairs. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 different arrangements or combinations of different ways you could arrange these marching band rows. And that is your factor pairs. We're actually going to go back to blue here because we have a little bit more vocabulary to talk about next. So this next word we're going to discuss before turning the page is prime factorization. So when we're dealing with prime factorization, one of these words, prime, is really important. We have to know. And factorization has the word factor in it, so that's important too. First, let's talk about prime. A prime number is a number that can only be divided by 1 in itself. So the only factors are 1 and itself. So an example of a prime number would be 3, because the only factor pair would be 1 and 3. Or 5. The only factor pair would be 1 and 5. Another one would be 11. The only factor pair is 1 and 11. So that's important to note. The next thing we'll talk about is a factor tree. So a factor tree looks like a little tree with branches on it with numbers, and this is going to help us get to the prime factorization. So it kind of branches out like this, and then it gives branches like this, and then it continues to branch off into different sections so that we can find the prime factorization. We'll do a little example here. So for example 2, we're going to write out the prime factorization of a number. Go ahead and change to green. So we have example 2. So now we are looking at page 27. Top of the page, example 2 says, write the prime factorization of 48. So if we start with the number 48, I always like to put that main number on the top. And then we're going to decide what is a factor pair, what times what would get us to 48. And there are a lot of different options. I'm going to go with 2 times 24. So we know that 48 can branch out to 2 and 24. Now what we're going to do is we're going to ask ourselves, are either of these numbers prime? Remember, prime only has 2 factors, 1 in itself. If we look at this, the 2 is prime. The only factors of 2 are 1 times 2. So we're going to circle that, and we're not going to branch that one out. So we branch numbers out until they become prime, and then we stop and circle them. 24 is not prime because there's other factors of 24. So we're going to keep 24 going on its branches. So what times what is 24? Well, we could go 12 times 2. And we know 2 is prime, so we're going to circle it again. 12 is not prime because there are other factors, so we're going to keep that one going. Let's branch that one out by saying 6 times 2. Oh, look, we have another 2, so we'll circle it. That's a prime number, and the 6 can keep branching out. To get to 6, we could go 3 times 2, and there's another 2. A 3 is also prime, so we could circle the 3 as well. So what we have here is now we have branched everything out until all the numbers at the bottom are prime numbers. We have a 2, a 3, a 2, a 2, a 2. We don't actually even worry anymore about these middle numbers. We only look at the prime ones because we're doing a prime factorization. If we listed all these numbers out in a multiplication sentence, this is what it would look like. 2 times 2 times 2 times 2. There are 4 2's. And times 3, 1, 3. That would be what it would look like in a multiplication sentence. If If I wanted to kind of squeeze that together a little bit, we could actually use some powers and exponents to do this. Since there are 1, 2, 3, 4 2's, we could write a big 2 to the 4th exponent, to the 4th power, and then we could multiply that by our big 3. This right here is the correct version of the prime factorization. So we took our big number and branched it out until we had only primes left on the bottom. Then we listed out our numbers with multiplication signs in the middle. And then we squeezed it together, simplifying it by doing bases and exponents. And this is what we have left. So that is example 2. So we'll move on to example 3. Let's go ahead and switch colors. Oops. Let's try this one. Example 3, I believe, is our last one for this lesson. And let's start on a new page. Example 3 says, what is the greatest perfect square that is a factor of 1,575? Because 1,575 has many factors, it is not sufficient to list all its factors and check for perfect squares. We're going to use the prime factorization of 1,575 to find any perfect squares that are factors. The prime factorization shows that 1,575 has 3 factors other than 1 that are perfect squares. So here's what we're going to do. On our directions, we are going to put greatest perfect square. That's the directions that we have been asked to find. And so on a test or anything in a class, if you were asked to find the greatest perfect square, this is the steps you would take. The first thing is to write your number big at the top, just like we did when we did our prime factorization. And we're going to go ahead and factor this out using the tree model. So let's see, one version of, you could do lots of different ways to get to 1,575, but the one we're going to use today is going to be 25 times 63. And if that didn't just come to you in your brain, that's okay. I'm kind of giving you that. 25 times 63 would give you to that number. Neither of these are primes, so we're going to separate this one out. The only other factor pair of 25 besides 1 and 25 would be 5 times 5. And actually 5 is prime, so we're going to circle both of those, and those are going to be done. 63. The way we get to 63 would be 7 times 9, and 7 is prime, so we're going to circle that one. And then 9 can keep going. The only way to get to 9 would be 3 times 3. And 3's are primes, so we'll circle those. So step 1 when you're trying to find the greatest perfect square is to factor the number out until you have all primes on the bottom. So if we take a look at the prime factorization, it has 3 different factors other than 1 that are perfect squares. If you look at these numbers, a 5 is a perfect square because you could go 5 times 5 would get you 25. So that's a perfect square. Then you can look at the 3's. 3's are perfect squares because 3 times 3 would get you to 9. That would work. 3 times 3, 5 times 5. We don't have 2 7's, so we actually can't use the 7 when we're trying to find the greatest perfect square. So if you take a look at this, there are 2 5's and 2 3's. Since those match up together, we can actually multiply those together to get 15 times 15. So 15 times 15 would actually give us a bigger number than 25 or 9. And in our directions up here, they're wanting us to find the greatest perfect square. 9 would work and 25 would work, but those aren't the greatest perfect square. So if we pair them up this way and get 15's, if I multiply 15 by 15, I would have 225. 225 is bigger than 9 and 25, so this one would be our greatest perfect square. That would work for 1,575. If you'd like to try a couple, if you have some time, there are some on your own questions in this chapter, or in this lesson. The first few are on page 26, if you look back to that previous page, 1 through 4. So pause the video and go ahead and try those if you have some time. Okay, answers for number 1. The factor pairs of 18 are 1 and 18, 2 and 9, and 3 and 6. Number 2, the factor pairs of 24 would be 1 and 24, 2 and 12, 3 and 8, 4 and 6. And number 3, the factor pairs of 51 are 1 and 51, 3 and 17. And then the what if question says the woodwind section of the marching band has 38 members. Which has more possible arrangements, the brass section or the woodwind section? And the answer is the brass section. And the explanation is the number 38 has only 2 factor pairs, 1 and 38 and 2 and 19. So there are only 4 possible arrangements with the woodwind section. 1 row of 38, 38 of 1, 2 of 19, or 19 of 2. Next, go ahead and look at page 27. 5, 6, 7, 8, and 9 are on your own at the very bottom of 27. Go ahead and pause and work on those if you'd like. Okay, answers to number 5. The prime factorization would be 2 to the second power times 5. Number 6 would be 2 to the third power times 11. Number 7 would be 2 times 3 to the second power times 5. And number 8, 2 times 3 times 7 times 11. And number 9, what is the greatest perfect square that's a factor of 396? That would be 36, because 6 times 6 would give us 36. That would be the biggest possible way to get to a perfect square. And it does not matter which order when you write a prime factorization in. So you could rearrange the numbers in your multiplication sentence and still be correct. And that's it for our video. So page 28 and 29 is going to be where we pull some practice questions from. And we'll do that in class. Any extra ones that we don't do in class, you can go ahead and practice at home with.